Okay, I think it was on the slide, but I forgotten to point you to this. And basically, there's an abbreviation that we have for entailment. So basically, the idea was that we write down, we have a knowledge base, and this knowledge base is a set of propositional formulae. Here we are. The knowledge base is a set of propositional formulae, and we have some formula, phi or whatever I want to call it, or psi in this case, which is entailed. So the definition was that all the models of psi are a superset of the models of the knowledge base, or psi is true in all the models of the knowledge base. Yeah? So this is a symbol. It's this bar, and then the equality sign behind it. Yeah? So this was a semantic notion, which is now something we try to find algorithms for. And the algorithmic notion that we have is logically following or inferencing. So we now have also the notion, that's what we're going to work on now, which is this one. So let's use the same. Yeah. So you need to understand that these are two completely different things. This one tells me something about the relation of the models of the formula in the knowledge base. And this is algorithmically. So can I find a calculus that helps me derive that phi is true or whatever? And ideally, I want to show that these two things are exactly the same. So my algorithm calculates something that is the same as what my semantic notion gives me. And the goal of the second half is now to give you an algorithm that does exactly as the semantic notion we have defined before. Yeah? So we're now looking at calculi, namely the algorithms for inference. And I said this is the ideal scenario where they do exactly the same thing, but it's not necessarily the case. So we have a notion of soundness. Again, this is a definition. This is something you don't sort of understand a priori. You just need to learn those notions. And the notion of soundness is that whenever I say phi follows from the knowledge base, my algorithm tells me, yes, phi follows from the knowledge base, then it is also true. It only gives true answers. There might be phi formula though, to which it gives the wrong answer. Sorry, in which it doesn't give the right answer. It simply doesn't give an answer. It might not get all of them correct. Yeah? So that is the notion of soundness. It's a correct algorithm that whenever the algorithm says something follows, it really is entailed. Then I have a complete algorithm that tells me whenever something is entailed, my algorithm also gives the answer that it is entailed. Can anybody give me an answer, a simple algorithm for a complete algorithm to do entailment in propositional logic? So I test you now. I think you could, if you have the right strategy, you could give me a complete algorithm for doing this. So is the formula, take any kind of knowledge base. You don't even need to know the knowledge base. Yeah? My question is now, is the formula A and B entailed? No, sorry, does it follow? No, sorry, I want, tell me whether this is not, you are the algorithm, you just have to can say yes or no. Choose yes or choose no. If you consistently choose yes, you just say yes to all of them. So whenever there is a correct one, it will be indeed have the right answer. So it's a complete algorithm. For all the correct ones, it says yes, because you say yes to everything. Yeah. So this algorithm that he says yes, every time is a wonderfully complete algorithm. It's obviously completely useless. So completeness alone, what is that? Okay, might have pressed the wrong button. So the notion of completeness alone is completely meaningless because you just say yes to all the questions, and you, of course, with all the correct ones, you're right. The question is how many of the ones that you give are actually correct, and it wouldn't be sound because you are very often, in most of the cases, you're actually wrong when you always say yes to this question. Yeah. So what we're looking for is a algorithm that is both sound and complete, so that does both directions. Yeah. Soundness would be this one. Completeness would be this one. And we really need both in order to have a good algorithm. What actually helps as well if you write an algorithm if it terminates. So there is, for this first order logic that I was talking about, there is an algorithm that eventually stops. The only problem is you never know when it stops. It could be in 3,000 years, it could be in 1,000,000 years. We can never say that it should stop now. So in this time, we have even a termination that is quite good, but not good enough. But there are even algorithms that never terminate. Remember the algorithm of depth first search when you don't do duplicate detection. You just follow down the algorithm. You search, and you go back maybe in your circles, and you don't watch the circles. You have an infinite algorithm. Your algorithm will never terminate. And this can also happen in these logics. So we need soundness, completeness, and termination. And once we have that, we can decide, as it's called, a logic. We have an algorithm that tells us for any formula phi in our language whether it has a certain meaning or not, whether it's entailed or not, basically. We can reduce it in many cases to that question. So we're now looking at a sound and complete and terminating algorithm to determine in propositional logic whether a formula is entailed or not. And basically how we do that is we search for models. And the idea is the following, that if you have entailment, that you can show that this is the same as, so remember this notion, we want to do knowledge base entails some formula phi. And this is the same as to show that knowledge base plus the formula negation of phi, so this should be the same, negation of phi is unsatisfiable. Yeah. What was the notion of unsatisfiability again? It was that there is no model. Yeah, so we simply can't find a model for this set of formulas. That's basically something we as humans do quite regularly, that we say, suppose that this would be true, then we are inconsistent, so we can conclude that this thing cannot be true. And this is what you do here. You do a proof by contradiction. We assume that the thing we want to entail is false, and then we just have to show unsatisfiability. And unsatisfiability, as I said, is the fact that there is no model. So all we have to do is to search for a model, and as soon as we find a model, we're done, because then we've shown that this thing is satisfiable. As soon as you find one model, you're done. And if you've shown that all your search after you terminate didn't find a model, then you know it's unsatisfiable, and then you know we have entailment. Yeah? So basically the question of determining entailment between propositional formulae or sets of propositional formulae can be reduced to the question of, do I find a model for a set of formulae or not? Okay, let's do that now. And remember the example from the Wumpus world. We had some facts, so we knew our propositions, there's no pit in 1,1, so non-P11 must be true. non-B11, there's also no breathe. We know a breathe and 2, 1. So these are the facts of our game. And then we have the rules. So pits cause breezes in adjacent square. And we have for all of those squares, remember that this really becomes huge immediately. We have to do for all of the squares in the game, we have to write down the statements. So we've now done it here for P11 and P21. For the whole game, you would have to do this for all the 16 fields and for all the different properties of the game. Okay, this is enough for an example. So this is the rule that a square is breezy if and only if there is an adjacent pit. So now let's look at the notion of entailment first. And the idea was that we look at all the models for the knowledge base. Yeah. Remember, we're not talking about those 4 on the left-hand side. But now we have all those many values for all the combinations of bits and breathers, and we can give values to those. Yeah. And all of this is in order to show whether not P12, so safe 1, 2, can be and is entailed. So basically what we want to do is we want to find which of those things here is a model for the knowledge base, so consistent with all the axioms and all the information we have, and then check whether in all those non-P12 is false. So now basically I'm showing you an algorithm for doing this, and it's not a good algorithm, I tell you now, because it's very inefficient. It's not very, but it's one way of doing this. And that is basically that we look at all the variables, and we have now 2, 4, 6, 8, 7 variables, and we systematically enumerate all the truth values that they could have. So we could say B1, 1 is false, or let's say in the first row we just show all of them are false, and then we start with the last one being true, and then we do this for all the rows, and we do systematically through all the 2 to the power of 7 possible combinations of values. That's a lot. I can't calculate in my head how much that is, but it's a lot. So this is only a small part of this table. But now let's check which of those are the ones that are consistent with our knowledge, which are the models. Yeah? Let me see whether, no, I don't have it. So what do we have? There is no breeze in B11. So we can already exclude everything where B11 is true. So no, so you see that all of those can already be ignored where B1 is true. We also know that there is no pit in 1.1, there is no pit in 1.2. So all those have to be false. And whenever there would be a true value, we can discard it. So basically, where you find those dots, there is a lot of things that cannot be the case. And all the models that we can find, we know that there are 4 of them, because that's the thing we did before. Is basically now looking up which is for example, this situation. So we have pit 1, 2, those 3 are false. Anyway, so I think these are the models we are now looking at. So here we have which of them is a model for the knowledge base, and you basically get these 3 out. I think we have a bit more information than we had in the previous example, so we just get those 3 models here for the knowledge base. And basically what we now only have to do is to check whether in these 3 models of the knowledge base, P12 is false. So in those 3, we now check P12, and it's false at all 3 of them. So basically, just by enumerating, going through all those 2 to the power of 7 examples, we find the ones that are consistent with the knowledge base, the models, and we check in those models whether our thing that we wanted to have entailed is true or not. This is now not yet implying this method. We use that later. So this was really only what's called model checking, and it's basically this very, very simple algorithm. You take an assignment in the truth assignment, your assignment or a partial assignment, PA stands for partial assignment, and if one of them makes my formula true, then you return satisfiable. Otherwise, you return unsat. And sorry, this is not the algorithm I explained before because that was for entailment. This was far more complicated. We've now moved to the related notion of satisfiability. I'm sorry. I have to go one step back. The previous slide was really entailment. And now we move to something that's algorithmically easier, which is the notion of satisfiability. And if you now turn the idea around here, and if we would look at satisfiability here, what you would do is, in this example, you would add the negation of this to the knowledge base. Yeah, so that's this case, and then check whether you find a model for the knowledge base and the formula itself. And in this case, we only have those three, and in all three of those cases, the P12, the negation of this, would be false because the thing itself is true. So basically what we could show here as well, that this is unsatisfiable. So if you take the knowledge base plus the negated thing you want to show attainment for, then you would find that the whole thing is unsatisfiable. So there are two methods for now proving this attainment. The direct way is to just go through the table and find and show that in all your models the formula is true. That's what we did here. An alternative way is to use this trick and reduce things to satisfiability and unsatisfiability. So from now we make the step from attainment to satisfiability. And trust me, the one can be reduced to the other, so they both have the same purpose. But just looking at satisfiability is a simpler one. So that is basically now looking for a specific model that is consistent with the formula. And then the algorithm is just go through the assignments in a truth table systematically from top to the bottom, check whether one of them makes the formula true, and if it does, it's a model for the formula F. And that's what the pseudocode does, nothing more. And if it goes through the whole table and it doesn't find a model, then the formula is unsatisfiable. So basically then we have not for attainment, but we have proven that something is a calculus for satisfiability. There are two different ways of now showing this satisfiability. The one is that you really try to search for a model. We're going to look into one of those methods now, and this is basically one of the search algorithms we've seen before, even with heuristics. So these are the complete backtracking search algorithms based on a principle of Davis, Putnam, Lowland, and Loveland. And this is what I'm going to show you in the last half hour. Then there are some incomplete methods, and there are some methods based on rules. And we're also going to look into that tomorrow. Yeah? Before we can start doing that, we need some pre-processing. And this pre-processing basically means that you want to bring all your formulae into one standard form so that you can more easily implement the algorithm on just one specific form. And this one specific form is called the clause normal form. It's also conjunctive normal form, so you can remember also where the C stands for. And it's a conjunction of disjunction of literals. Yeah. So basically, this is an example for a conjunctive normal form. We have only negation in front of literals, so atoms. So, we only have negation in front of atoms, so propositional letters. So negation is not outside any other operator anymore. It's only in front of atoms, so the propositions themselves. And then we have disjunction of those atoms or negated atoms. And those are then conjuncted together. So basically you can look like them as some constraints where all of those constraints have to hold. So either A or B and not A or C. And so you have a list of constraints that must be satisfied, but in all of those constraints you have a choice. And the nice thing is now that every formula in propositional logic can be transformed by a very simple algorithm into this closed normal form. Right? This is this very simple algorithm, and it's just something you need to practice in order to be able to do it relatively fast in an exam. That's the first step. So you have 5 rules. The first one is sort of forgotten. It's an easy one as well. But if you apply those rules in the right order, you will end up in closed normal form. Yeah. In the corner it says, what do P, Q, and R stand for? These are just variable names that stand for any complex formula. So they are not, in this case, not atomic, but they could be any complex formula. Fine. Yeah. And then basically you start with writing, rewriting, and as I said, there's one that is missing that should have been the starting point. And that is the one where you have where you have some formula phi is equivalent to some formula psi. Yeah, that's the first one you have to rewrite. And if you find a formula in this, what you have to do, you just delete it and you add this and psi implies phi. Remember that when I introduced the semantics of this equivalence, it is bidirectional implication. So 2 things are the same if one of them implies the other and the other one implies the thing itself. Yes?
Is that step for the first one?
Yes, it's a first step. Yeah, sorry. Let's call it step number 0, and then we are complete. Yeah.
The CNF is conjunction of disjunctions, thus implies.
Sorry?
The CNF, the last normal form, is conjunction of disjunctions.
Yes.
So it's not implies. There's one implies the other.
Yeah, but this is step number 0, and then we have a thing that gets rid of the implication. Then we have a step that gets rid of negation. And then we have a step that gets rid of the disjunction in the negations. So that's basically what all the rules do here. So first you get rid of all the equivalences by replacing them with implications. Yeah. Then you look at this one, P implies Q, and you just replace it by the negation of P or Q. And you can prove with your truth tables that they actually are the same. So it's just semantically, it's exactly the same. Yeah. Here we are just looking at this from an algorithmic perspective. We just use this as a rewrite rule from a formula to some other formula. You just replace the one by the other. Yeah. So the first one is you replace the implication. The second one is you move the negation inwards. So if I have a negation Q or P, then I rewrite that to negation of P and not Q. So I put the negation inside and I turn around the operator from negation to, from disjunction to conjunction and vice versa. Yeah, it's just don't forget to turn around the operator in the middle when you apply the algorithm. The third or the fourth step is 3 here. And that is distributing the disjunction over the conjunctions. And these are rules that we all familiar with from algebra in school, where you do exactly this over. If you have 3 times 5 plus 7, then you also distribute it over the rules, I think. And then the last thing is that you need to split the conjunctive rules and you turn them into some kind of sets or so. But you don't need to do the last step. It's clear enough. The idea is that what I showed here, I skipped over that a bit, that there is some mixed forms of writing it down. So if you basically want to implement reasoning with logic, you want to put your formulae into lists or into sets. So you don't want to have a symbol or between. As we know that, this is more easy to implement because it basically you put not C, not B in a list and C in a list, and you don't need any complicated data structures. So the idea is that you reduce a formula to a list of a list, yeah, and then it's very efficient to reason over it. So just iterate over the objects in your list. And that's why there is the effort made here to get rid of the logical operators for the calculus so that it's easier to implement. And you're right, I should have, this is a mixed form. So I put it in sets of formulae and not sets of clauses. You're right. So in principle, this is half of the way to this bit up here, where I left the disjunction here. So let's look at an example. We start with this equivalence. B1 is equivalent to some disjunction. I use this rule to eliminate the equivalence, and that is basically just add this formula in one direction, and then I turn around the order, and I have another implication in the other direction. The next step is eliminate the implication, and remember the rule is that alpha implies beta. Then we have to replace it with not alpha or beta. And we do that here. So we have non-B 1, 1 on this side, or and then the right-hand side of that. And here we have the second part as well. We have to negate this bit, which end up here, or not B1. And now all the implications have gone. The next step is the De Morgan rule, where I put the negation inwards. So remember, you have to turn around the operators and then put the negation signs inside. So here we have, this is the De Morgan. We have to get the negation inside. Guys, please, 15 minutes. So now we have to negate P11, and we have to turn this one around. So we get this statement. Now we have to distribute the conjunction over the disjunction, which is on this side. We have a conjunction. So basically, we get those three clauses. Yeah. And in the interest of time, I leave this out now. Maybe if I give it as homework. So please do me the favor. Take this. There isn't even an equivalence. This is the kind of things you can expect in an exam. You get a formula, and then you have to apply the rules. And this is something you can practice by your own. I don't think this is the most complicated thing to do. Yeah? So it's basically applying one by one the rules as they are written here. Yeah? Okay. What I want to get in is the first version of doing this whole thing more clever. And this is the Davis-Putnam procedure, which they came up with in '62. And this is now applicable on clauses. It's also applicable on formula in general, but we work on clauses now. And basically the algorithm is as follows. You check for the algorithm. The first version of DPLL is you take a partial assignment. So you start with the value for one of the propositional variables, and you check whether this partial assignment is already sort of makes your formula that you're evaluating false. And in that case, you just return false. So I have a formula. I want to check whether it's true or false. I guess some value for a propositional variable. And if it's false, then I just return false. If it is true, then I return true. So as soon as I can really decide whether my assignment is a model or not, then I return the truth value. In many cases, I can't do that because the idea is that I start with the smallest variable assignment, so assignment of variable value for one of the variables, and then I do that iteratively for all the propositional variables. until I find one which makes my formula either true or false. Yeah. So I choose one, some random or informed proposition and variable to evaluate further, and then I just give this back to the abstraction procedure. So it's a recursive call, and I check, okay, now that I've added a variable, calculate for me whether on this new partial assignment it is true or false. Yeah? And if that is the case, then you return true, and otherwise you return the result of the other choice for P. So here it is 0, 1. That's a sort of notational bad habit for someone working with this. I don't really look at this syntax anymore. This should have been P is true and P is false. So you can use letter T, word true, or numbers 0 and 1. It always means the same. 0 stands for false and 1 stands for true. So here basically you decide that P should be false, and if then the recursive algorithm gives you an answer, you return true to that. Okay. So that's quite difficult to understand. So let's look at an example. So this is the first version of the algorithm that I've showed you before. And this is our knowledge base. So we have 4 clauses, and they all must be true. So it's a conjunction of these 4 clauses, A or B or C, A or not B, A or not C, not A or C. Yeah? And what the algorithm does is that it starts with one variable, and it makes a decision on whether it should be true or false. Yeah? And then it continues with the decision to make the next one. So the red one means to give the value false to a variable. Yeah. So I had to check that. Sorry. So the first thing you do is that you assign a value false to A. Yeah. So that is this red error that happens. Yeah. I start with the value false, and then I have to check, is my formula now satisfied or not? Okay, so this one, it could still be true. They could all still be true. So nothing has broken yet. Okay, so then I have to look deeper in the tree. So now I take variable B, and again, I assign a value false to it. Yeah, so what happens when I assign the value false to B? I don't know about this one. I don't know whether it's true or not, the first one. I know this one is true now, so that's good. I know this one could still be true. I don't know. And the last one could also be true. So I haven't decided yet whether the thing is satisfiable or not. So I need to continue. So I need also to give a value to C. I give the value C in my search. And now I realize that the first one is a contradiction. Yeah? Okay, so my guess, my search for a model failed here. So false, false, false failed, because the first one is not satisfied anymore. The first clause is violated. So then I try to assign value true to C. But then I see that this one is violated. Yeah, because A is false and C is true, violates this third one. Okay, so then I have to go back, which is called backtracking. And that means let's assign a different value to B. Let's assign true to B. And then we have A is false, B is true, and that violates the second one, of course. So we have to backtrack on A. So A must now be true. Okay, so that doesn't violate anything. So let's go on in the algorithm and decide for B. B is false, is the first choice, still possible. So now let's decide for C. That violates the last one. Let's try C to be true. That does not violate any of them, so that's consistent, so that found as a model. Yeah? So now the choice of A being true, B being false, and C being true gives us a model, because it finds a variable assignment for these 3 variables that is consistent with all the axioms in the knowledge base. Yeah? Yeah?
Why does it violate the third one?
Because A is true.
And C is false.
Yeah, that's a very fair point. So it's not a model, I think.
A is true, so it's true.
Oh yeah, it's a disjunction. Sorry. So either A has to be true or C has to be false. And as A is true, this formula is true. Thanks. Sorry, it's a bit. Yeah. So only one of them needs to be satisfied. Here, only one of them has to be satisfied. So probably you could already have stopped here because assigning a value A. Oh no, this one wouldn't have satisfied this one. Yeah. Okay. Yeah. You really need to do all those search steps. Okay. So yeah. Oh, you have to decide on this because then the example works better. But it's in a way this is your choice. You can and we will even see in a minute if I have time. Otherwise tomorrow that choosing the right variable is one of the core decisions to take. And if you there are heuristics for where should I start, and that's exactly something that guides us through the search process. Yeah. But still, we have some more things we can do in order to reduce the size of the search space. That's now the next steps. And here's some ideas. So if I have a literal, which is either an atom, so a propositional letter, or its negation, and if I can make those one true, then the whole clause is true. So that's an observation, and we can make use of that. So it is okay to delete clauses that contain true literals. And we have also ones where we know that they are false, then we can shorten the clauses. We can just take the one thing away. So if I have A or false or C, then nobody would ever choose false because then the formula would become false. So you can get rid of that. So if I know that an atom is false or literal, I can just get away, leave it out. Yeah. And it means the empty clause, so if I don't have any choice, then it's always false. And these are observations that I can make to improve the algorithm. So basically, if I have a negation of a literal, if I give a literal with it, and I know that something is, so basically if I know that A is true, for example, I can remove all the clauses where that contain A. Yeah, that's because we have the constraint of A or B. And then if I know that A is true, then this is not a constraint anymore because it's always true because of the A. So I don't have to care about the B anymore. So this is now very powerful because now we can run the algorithm again. So we start with choosing A false. Again, this is an arbitrary choice. But now see that we can now simplify our clause set because of if we know that A is false, we know that it will never play a positive role in these constraints. Yeah. So we can simply, in all the clauses that we have, remove all the A's. Yes. And even more powerful, we can remove the ones where not A occurs because we know it's true. Not A is true if A is false. And then we can remove all the clauses in which this literal occurs negated. So that's a very powerful idea because now we've made one choice. And by this one choice, we've reduced our clause set that we have to check. Okay, now let's take the next one. We can now take B negative. So we know that the second clause goes. And we have only these two things left. So the next thing is now we have to decide whether C is true or C is false. And as you can see, choosing either of them will give us a conflict. We can backtrack on B, which is also much faster. And then the next thing is to go for, if A is true, then we only have one variable, and that is C. And basically, we can take any value for C, for any value for B, and we find this far faster. Okay, so that's the one variant, but there's even more to gain, yeah? Because if we know that we have clauses that only contain one element, the unit clauses as they are called, we know immediately what value my variable has to take. So if I know that in one of my constraints it says not B, then I would be stupid to choose the value B, because obviously B has to be false, because if I don't have any conjuncts left. And the other thing is, if there is one variable that occurs only negated or only non-negated, I can only make the choice of choosing either of them and change the thing. So basically the algorithm now becomes more complicated. It says if it contains a unit clause or a pure literal, then start with this and eliminate the smallest, namely the one length of one clauses, eliminate them first. Yeah, so that's a very important change now. So let's look at our algorithm again, and that's the final version of DPLL, which is now really powering most of those tools. Basically you start again, negated A. That gives you, again, the shorter closing, because you delete the last one and you delete the letter A itself. Now we have the unit clause, because now we have two clauses in which there is only one literal. We have two of them, namely not B or not C. So now we should really immediately start with B being true, because we know that, B being false, because we know that there is no alternative that it could be true. So we choose B to be false. And we know here, so that's not an important step. Let me see why this happened. We now see that we don't even have to look at B anymore, because this has already been excluded here. So we can do the backtracking immediately directly to this other case. And now we know that we only have to look at the case where C is true, and we find the solution. Yeah. So the choice for not going for B here was made on the basis that there's only one variable here, which is C, and we need to do the unit clause thing, and we don't have to check for non-C, because we know that C has to be true. Yeah. So basically now we have the same thing. We found the model, namely that A must be true and C must be true, and B we don't even care. We found a model with only these two steps in the search tree. So this is now the algorithm, the real Davis-Putnam algorithm. As we've seen before, the choice of which variable to start with is something where we can use the heuristics. So, and one of the ideas for using is called, for example, what is called the MOM heuristics, where you say the most occurrences in clauses of minimal length. So you look at the shortest clauses, and then you tell how many, you count in how many the variables occur of those short clauses, and you start assigning values to those first, because they will get you to the unit clauses first. That's, for example, a heuristic that you can apply in order to shorten the tree even more. And I think that's a good slide to stop with. You can, with this technique, I said that we had the complexity of 2 to the power of 7 if you go through the whole tree. And you can now reduce this to, I think, 2 to the power of 3.5 or something with Davis-Putnam. So in practice, this really allows you to have many more variables you can do reasoning with. And if you apply this algorithm of Davis-Putnam, you basically now get an algorithm that does this for you. So if you have Davis-Putnam here, then it gives you the answer to your questions. Whenever they are correct, you get the correct answers. And I showed it now for satisfiability. I will show you tomorrow how to translate this into attainment, which is very simple. But the basic idea of this algorithm is really to reduce the search space in the search for models with the methods that we've seen before, some heuristic depth first search. And that was it for today. See you tomorrow. Thank you.